Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to talk about another smart material which is popularly known as shape memory alloy. So the shape memory alloy is one of the latest inclusions in the brand of smart materials, which has phenomenally dramatic properties in terms of the actuation strain, in terms of the force. In fact, people actually compare it with something like an artificial muscle. So let us look into that what is there in this artificial muscle, what gives these such interesting properties. So I will first talk about what is shape memory effect, then I will say what are the metallic alloys that show the shape memory effect. Then there are three important properties of shape memory alloys. One is called one-way shape memory effect, another is called two-way shape memory effect, and the third one is called pseudo-elasticity. So these three things we will discuss. Finally, we will talk about the applications of the shape memory alloy. So let us first see what is this shape memory effect. There are certain classes of metallic alloys which have a very special ability. This special ability is to memorize their shape at a particular temperature, and then what you can do is that if you actually if it undergoes a large deformation at a low temperature, the moment you thermally activate it, then once again it will get back its shape. So I would rather say generally it is to memorize the shape at a high temperature. In fact, in case of a two-way effect it is both low and high, but otherwise it is at the high temperature, and then you bring it to low temperature, do whatever you wish, the large deformations. Finally, as the thermal activation takes place, you will see that the same shape is back again. So this effect was first observed in 1932 in actually gold cadmium alloys. There are three types of SMA that are currently popular. One is copper zinc aluminum, another is copper aluminum nickel, and the other one is nickel titanium alloy. So it's a binary alloy in comparison to the other two, and since 1962 this was discovered, it is becoming more and more popular. So the last one, this NITI, is actually commercially available with a name called nitinol, that is nickel titanium Naval Ordnance Laboratory of USA, who have actually discovered this particular shape memory effect in this particular material. Now let us see that what is the competitive advantage of this shape memory alloy. If you look at it, that the maximum specific actuation stress wise, SMA can give you something like 0.1 meganewton meter per kg, and the actuation strain is about 0.1. On the other hand, if you look at PZT, it is actually 1,000th of this capacity of 100th of this capacity of the SMA, and actuation strain wise it is 1000, is very low. Now if you compare it with human muscle, even then the SMA is actually quite high, because human muscle is 0.005, so it is quite high, and the actuation strain wise, however, the human muscle is much above the SMA. So stress point of view, if you compare SMA with the capability of SMA as an artificial muscle, then from stress point of view it is well above the human muscle, but from strain point of view it still has to improve a lot. On the other hand, with respect to any other smart materials, it is much far ahead. Now there are two common shape memory effects. One is called one-way effect and another is called two-way effects. In the case of one-way effect, the material always remembers the shape at parent state, and that is the austenite phase. That is what I was telling you, that at the high temperature austenite phase, it remembers that in the case of one-way effect. However, in the case of two-way effect, you can train the material in such a manner that it can remember two shapes, one at the parent austenite phase and the other at the martensite phase. So this, however, you have to give lot of training to the system. How do we manufacture SMA, particularly in the wear form? So SMA are typically first made by casting using vacuum arc melting or induction melting or similar such processes, but both of these processes are highly specialized process and very highly expensive process. However, these techniques are used to keep the impurities in the alloy to a minimum and ensure that the metals are well mixed. So once you are actually using this process and you are making this at a high temperature, you are mixing this and then you make the ingot, then you hot roll it into longer sections and finally you draw it into wear form. So that is how we actually manufacture the SMA wear itself. Okay, so this is just not simply SMA but the SMA wear itself. Now the crystal structure point of view, there are two crystal structures in SMA. One is at high energy or high temperature form and another is at low energy or low temperature form. So at high energy, the form that we encounter is called a body centered cubic structure, austenite phase. Okay, so here the nickel and titanium atoms, as you can see in this system, and in the face centered you get it in the face centered form of the system. Now these are the two crystal structures. How does it behave? Let us say first we consider the low temperature stress strain behavior. So at the low temperature level, that means it is at martensite. So this is at the martensite phase. In fact, it is initially at the twinned martensite phase. Now as I am increasing the loading, after a certain point it will start to detwine. That is the first yield point. Okay, so I have crossed the elastic region. Now the transformation is happening from twinned to detwined state. So beyond this, this detwined state has been achieved, as you can see, and then once again it will behave in an elastic manner. So that is the elastic region. After that twined shape, if you do not change the temperature, then you will see the yield region and the failure of the system. So this is the low temperature stress strain behavior of the SMA wear. And what about if I only change the temperature? So if I take SMA wear and if I only change the temperature, let's say, so what I will see, if there is a way I can continuously monitor that what is happening to the internal material property chain, I would see that initially till about if say for example austenite start point, so I have to go up to this point, I would see that the material is at martensite formation, which is the FCC formation, and then as I am hitting this martensite is now getting converted and it is now becoming austenites. Okay, so it is taking the BCC form. So AS, this is starting, and at AF this is over, austenite finish temperature. After that, if I increase the temperature, it will be 100% austenite. So 0% austenite initially, and after AF it will become 100% austenite. Again, if I now reduce the temperature, what will happen? Initially nothing will happen, But then as I decrease the temperature at MS, suddenly it will start to cool and the martensite now will start to form. So martensite formation is happening more and more and more until we reach the point of MF. Here, the martensite formation is over. There is no austenite left in the system, provided I have not touched the stress profile of the system. If I touch that, then of course the situation will be more complicated. But let us first talk about the one-way shape memory effect. So in the one-way shape memory effect, there are two types. One is the beam extension, another is the beam bending. Let us first discuss what happens in the beam extension. Suppose I take a SMA sample which is at the austenite high temperature phase. Then I just cool it, fine, and then it goes to the martensite low temperature phase, but there will be no change of length. Okay, so that means even though there is this twined martensite formation that has taken place, but it is internally adjusted procedure, so there will be no change of length. Now you deform it. As you deform, the length got increased to L0 plus delta L. But here it is from the twined to it has become detwined martensite phase at low temperature. Now you heat it up. As you heat it up, you are once again going to get back your L0 at the austenite high temperature phase, meaning thereby that every time you cool it, do whatever you wish, and then once you heat it up, you come back to this austenite high temperature, you are going to get back that same length again and again and again. That is what is the one-way shape memory effect. What happens in terms of bending? Pretty much similar. Suppose I have a particular beam here which is deformed with the help of some kind of or due to some kind of an external loading. Now it is at the austenite phase. So this is at the austenite phase to begin with. Now I am cooling it. As I cool it, there will be no change. As I told you that this martensite is actually twined martensite state, so there will be no change. Internal adjustment will be there. There will be no change. Original shape will be there. Now suppose I change the load, then there will be a deformation, the change of curvature immediately, as you can see, that is going to happen to the system. And now if I heat it up, what will happen? It will once again, no matter whatever is the load, it has to go back to that original shape. So it will once again regain that original shape that was there in the system. So that is the beam bending effect, one-way shape memory effect in the beam bending. So this is now in terms of three-dimensional situation. Okay. Now there are two things that means. One is called the Bain strain, which refers to the atomic rearrangements, and another is the lattice invariant shear, which refers to the release of a large amount of strain energy. Now if I have to follow that, I have to look into now the combined diagram of stress, strain and temperature. So far for all the materials you have only seen the stress strain behavior, but now temperature has also come into the picture. So let us say I have taken a material which is at its original point number 1, okay, and then I am loading it. As I am loading from twined martensite, so this is the twined martensite state. As I am loading, I am detwining it, and then it is coming completely detwined phase. Now after that, suppose I don't want to fail the material, so I only reduce the load. If I reduce the load, it will come back to point 3, in which still there will be lot of plastic strain that will be there in the material. At this stage, I leave the the planar stress strain part, and I start my new heat axis, and I start to heat it up. As I heat it up, gradually you will see that the strain will vanish. At this particular point of time, it has F region, it has already gone back to its original shape. Now in that original shape, if you cool it, it will remain in the original shape, but if this is austenite here, from austenite stage it will go to the twined martensite stage. So this is the three-dimensional change that happens to the system. In fact, the left side also we have shown you the same thing, austenite BCC phase, and then you cool it, you go to always twined martensite, you deform it, the twined martensite becomes detwined martensite, you heat it, and you are going to get back your austenite shape or your memory shape. Now if suppose I do not change the temperature, I keep the temperature at a high temperature level this time, not at low temperature but at a high temperature level, and then that means to begin with I am at the austenite level. Now at that level, if I load it, what is going to happen? It will straight come down to the detwined martensite phase, and then if I unload it, it will straight come back to the austenite phase. So you are not coming via the twined martensite state anymore. This kind of direct transformation from austenite to detwined martensite phase has something very peculiar in this stress-strain relationship, which is known as pseudoelasticity, and this is highly used in structural damping. Let us see how this will be useful. If I look at the pseudoelastic behavior, that means here I am at austenite phase, and then I am increasing the load, okay, up to point 2, the elastic loading is over, suddenly the phase transformation happens. This is stress induced phase transformation, and I am going back to the martensite phase, and then from that phase I am reducing the load again, and then if I reduce it first, initially it is once again elastic, and then the huge change, and it comes back to number 5, and then if you further reduce it, it will be at that austenite stage itself. So interesting thing is that this loading and unloading at a high temperature has this much of area covered by it, and this area is responsible for the hysteresis, or for that matter for structural damping. It is heavily being used today now for structural damping. So this is the pseudoelastic effect. Now you need not always go to the full cycle of complete austenite transformation. In that case it may happen that you increase the load, partial transformation has taken place, you unload it, once again it is going back like this. So this is what is partial pseudoelasticity. The difference between the two is that for complete pseudoelasticity you start from 0 and then you can come back to the 0 strain level almost itself. That is complete pseudoelasticity. If the temperature remains between AS and AF, then you get partial pseudoelasticity. If the temperature is greater than AF, then you get complete pseudoelasticity in the system. Now there are many commercial applications of one-way SME. For example, this is a Reshem Corporation product which is known as Cryocon. It is essentially a connector which is used for joining tubes in aerospace applications, and it takes the form of an oval ring of SMA set at martensite phase at low temperature. So initially this is an oval ring. Now when cryocooling is removed, that means from low temperature when you are coming back to high temperature, the ring gets circular and squeezes the tubes and join the two tubes. So it starts from an oval shape, you fit it, and then you remove the cryocooling and it fit the two connectors. So that is cryofit and cryocon system. So this is one of the effect of one-way shape memory effect. Now in the two-way shape memory effect, it remembers both the high temperature shape as well as the low temperature shape, okay, which is which is generally not erased in this particular case. The secret for this is that you need to have a combination of thermal and mechanical cycle training so that it will induce the micro stresses in the material. Then only at the low temperature phase it will be able to go back to the exact shape that you have trained it to have. So then this would result on a preferential formation of twin variants in the martensite phase. So how will be the two-way shape memory effect? This is where you are the original shape at the martensite level. You deform the whole thing and then you heat it up. You are going to get to this particular shape. Now from this shape you cool it, you are going to go back to this particular shape, the bent shape. So now you heat and cool, you will be flipping between these two shapes. One is at a high temperature memory and another is at a low temperature memory shape. Using these, there are many interesting applications that has been developed. For example, the control of aerodynamic surfaces like aircraft wing controls, etc. As you can see here, that SMA wire is controlling these so-called angle of attack. So that is one application. Microcoils for vibration isolations or grasping by the robotic fingers, that is also done. Space exploration or rockets, rock splitting. Then development of nitinol filters or deployment of solar array hinges. There are many applications, particularly space applications of SMA. One such application is how to generate vibration. So what you do here is that, suppose this is a cantilever beam that you have. On that beam you have two sets of SMA wires. Now you actuate one of them, suppose this one, so it gets shortened, so this whole beam gets deformed downwards. And then you cool it and you start to hit the other one, so the whole beam will go to the other side. So then you do these processes again and again, and then you will see that there is a continuous vibration, of course at a low frequency, that's happening by the help of the SMA wire. You can also use these SMA wires for tuned mass dampers, where you have a primary mass and you have the SMA wires and then you have the absorber. The advantage is that for any tuned mass damper we know that there is a spring and a mass that is attached to the system. Now the stiffness of the spring and the mass, these two remains invariant. But in the case of SMA, this K can vary, and as the K varies, so the natural frequency of this secondary system, that square root of K by M, as K varies, then the omega S also varies, and then thus you can actually tune it to different frequencies. One of the fantastic application of SMA is a variable geometry chevron application, which is done by Boeing in Dreamliner aircrafts. If you next time fly in Dreamliner, you would notice that it's the edges near the engine, this is jagged. The reason being of this jagged shape is that initially at this phase, when it is at say detwined or twined martensite, but it is mostly martensite phase, at this phase it has this jagged shape, and this actually helps for vortices to keep the size of the vortices too low, so that it gets attenuated fast. Now as you are heating up, then this shape, and you are going up, then this shape will go back to a flat shape, which will increase the efficiency of the system. So thus you can play between the two shapes and then keep the aircraft really very less noisy. Another example is in terms of amplified SMA actuator. So here this is the SMA in the system, and you apply heat, Now because SMA can give lot of force, so you can deform an egg shaped system. So if you try to deform an egg by the semi-major axis, you will understand what I mean. It is very difficult, you need lot of force. But however, if there is a small deflection here, the deflection is going to definitely get amplified along this direction. That is what actually is done in this particular case as well. One very interesting application of SMA is in the form of SMA wire-based sensor that we have developed. So what you do here is that you take a kind of angle encoder where you have these contacts, and then these are actually conductive things, and these angles are drawn with a known angle. Now these two pins are touching the system and you are passing the SMA wire based current. However, the catch is that whenever these two pins are touching this the SMA wire based system, only then the current is flowing, and then because of that resistance you are going to get a signal. The moment it is not, or the velocity is changing, you are going to see there is a shift or a phase delay, which you can use in terms of measuring the direction and the angular motion of the system. So this is where I'll come to an end, and in the next lecture we'll talk about introduction to material selection and the ASPE approach. Thank you.